Good evening, everyone. Thank you for joining in a webinar after a kind of long weekend and still so many participants is a kind of honor to me. Thank you so much. Today I will be talking about optimization and genetic algorithms, and let's make it as informative and as interesting as it can get. And a small introduction about me from myself. So I am Sanjana, working as a data scientist in Continental Automotive. It's been a few years now in Continental, being data scientist as well. So it's nice to be a data scientist because everybody talks about it. Something which really interests me in the field is statistical learning and machine learning. So yeah, that's a small intro from myself. So moving ahead in the agenda, we have introduction and application of optimization, mathematical representation and characteristics of optimization problems, evolutionary algorithms, genetic algorithms, a small example code, and a few case study how a genetic or optimization algorithm is approached. So these are the things what you can expect from today's session. So let's get started. So at the beginning, let's hear a story. So what I believe is anything which starts with once upon a time becomes a story. So that's how this situation is called a story. So there was a company which produced and sold a new type of energy drink. So like any other business, the company's goal was to maximize the profits, but they were not sure how do they do it. They knew that they needed to find an optimal combination of ingredients, price, and advertising to make the most money. So how, but who will say that what is that optimal thing? We data scientists will say that. So the company's data scientists set out to find the best solution using optimization. So they began by gathering data on the cost of the ingredients, the prices of similar products, and effectiveness of different advertising camps. So then next, they use this data to create a mathematical model that predicted how much profit the company would make for different combinations of all these parameters, these set of parameters. This model was the objective function which they wanted to optimize. So then they tested for different combinations and used the objective function to evaluate the performance of each one. So after maybe several iterations and lot of brute force applied, they found one great combination which increased the profit. So, and as I told, it is a story, let's end it like a story. So, and then the company implemented the solution and it flourished and the data scientists were crowned. So this was an example of real world scenario where optimization can be really used. It's been readily used. So optimization is not something very new. When you see it just outside, everywhere people are optimizing. I start morning from my house to office. I am optimizing a small route so that I don't take this route. I will take the other route so that I reach office soon. So all those small things are also optimization. And when it comes to bigger scale, more complexities add up, and that is again an optimization, but the solution will just not be easy as we do in our everyday lives. So here I have top picks on definitions of optimization. These were one of my favorites, which found very catchy to me. So optimization is the science of making the best out of a bad situation. Definitely. So optimization is a process of making something as good as it can be. By Edward de Bono. I think he's like very famous, and you might have also read the book where he has written a lot about the thinking hats. And the next one is optimization is a process of taking something that is good and making it even better. Optimization is a process of finding the best solution from the set of alternatives. So all of these does make sense, and all of these are as good explanations for definitions of optimization. So let's move ahead and just try to understand or to peek inside a little more to understand where all optimization is used. So where all optimization is applied. I think when I have listed here, it has almost every field I know. So just I will try to give an example. If it is engineering, how and where and what are the optimization things engineering is doing. And definitely there are wide examples as well. So in maybe in engineering, optimization is used to design and optimize structures, machines, and systems by finding the best configuration of materials, shapes, and dimensions. So that is one of the, like a pain point of many civil engineers, be it design engineers of automobiles and so on. So optimization is very, very readily used. And in finance, optimization is used to find the best portfolio of investments to maximize profits and minimize the risk. So I think a lot of this generation is very familiar with investments and trading and stock market and so on. So to have a best portfolio about a company, about anything. So I think you might have also observed in a lot of platforms, investment platforms, you see it is a KNN based predictive model. So everywhere optimization is running at the behind so that it makes the platform more easy for you to pick up the stocks or pick up whatever investments you want to do. So all those information is coming readily. And also when it comes to machine learning, to train models and to find the best parameters, then minimize the error rate and improve the performance. So here we can assume it as maybe feature engineering, where we will have a set of best features captured to further increase the process of machine learning, or also to tune the hyperparameters to get the optimal result of an optimal values of the hyperparameters. That itself is the optimization of what we are doing in machine learning. Then in computer science, to solve problems in computer graphics and computer vision, a lot of pose estimation, traffic estimation, and everything is all a part of optimization. Robotics, control the motion of robots and to design robot systems, controllers, and so on. And in biology, used to model and understand biological systems such as maybe protein finding, gene regulation, and population dynamics, and what all the biology field is doing. A lot of optimization is adopted. And in the healthcare industry is nowhere behind in adopting technologies. So healthcare industry used to design and improve medical treatments, such as maybe drug design and radiation therapies and so on. And finally, transportation. So used to plan the design of traffic, control systems, and route planning, logistics, the entire fleet. For example, we have I sit in Bangalore, so we have a lot of delivery apps around us. So all of them have some fleet management happening in between, and everybody is competing in the that ETA. So they are they are improvising the optimized algorithm of the fleet. So that is one of the greatest adaptation of optimization according to me, and one of the complex optimization according to me. So these are some of the applications in my mind to give an idea about where optimization is used. So okay, now we spoke. Going to the next slide, I think my screen is okay. Okay, now we spoke a lot about where all optimization is happening. So now let's go deep and understand on generic basis how the problem looks and how we approach it. So this is a general framework of optimization. So the variables known readily from available data, unknown variables from maybe forecasted models or forecasted data, and all of these form variables as part of optimization problem. Then everything operates inside a system. We are a part of a system, be it corporate system, be it political system, be it a city system or whatever. So, so which will have a scope. They form the constraints. So variables constraints are a very integral part of an optimization problem. So constraints incorporate maybe the HR policies and so on. So we will operate inside those constraints. So it is the general meaning of constraints. For any problem, there will be scope defined. The upper bound and the lower bound is always defined. We operate inside that. So that forms the constraints. Then objectives. Now, what is my objective? What do I want to do? Do I have to minimize something, maximize something? What is that I want to do? So that becomes the objective of the optimization problem. So all these three things are put inside our algorithm, which finds the best solution that maximize the objective what we are looking for um, with respect to the constraints. It will never come out of the constraint and solve something. It is very important for us to take a serious watch that we are operating inside the constraint. So all of these are the inputs of the algorithm, and the algorithm does the job. So as we understand this, we'll move ahead and understand the components of an optimization problem in a little more detail to have a better clarity. So the objective function, maybe while in industry we just say f of x and become it that is objective function for us. So the first component is an objective function f of x, the function which we are trying to either minimize or maximize. So that is the objective function. And the decision variables. The second component is the decision variables, which we can choose to minimize the function. So we write it as min of f of x. What does this mean? What are we doing with that objective function? We want to minimize. We have a function. What we want to do with that function? Should we minimize the function, maximize the function, and whatever we want to do according to the problem statement, that becomes the decision variable. Then constraints. So as I told, there is always an upper bound and a lower bound, the scope of the problem. So that becomes the constraint for us. So we can write it as minimize f of x with respect to x lies between a and b. So this will be our problem statement. This is how we write an optimization problem. So then a stopping criteria. So stopping criteria, when do you want your optimization to stop? It because if you run, you can run it infinitely, but you want to capture the result from the optimization as well. So when do you want it to stop? After certain number of iterations, after certain number of generations, or a certain, if an objective function has reached a certain value, you want to stop it. So you have to also define a stopping criteria. How are you going to end your algorithm? So this is about the components of an optimization problem. So now let's move ahead and understand a few terminologies which are part of optimization. So in the first, we see the local maxima and the global maxima. So what is local maxima, and why are these terminologies important for us to know? So local maxima is a peak value in a function that is greater than its neighboring values in a specific region. So, for example, you are climbing a mountain. So there is a mountain ranges. You are climbing all those entire ranges of mountains, and there will be definitely one peak, the tallest point in the mountain. But there are several hills, are also mountains or hills. So they are also the peaks, but they are definitely will be greater or shorter than its neighboring. But it is not the greatest peak of the entire mountain ranges. So that is how you see local maxima and global maxima. Global maxima is the highest peak value in a function over the entire range of function. So, uh, so it is very tricky for us because we should be very watchful in what is our endpoint. Are we just stuck up in the local maxima or global maxima? So that is something which we have to be very watchful about. So then next, what happens if you are stuck in a local optima? So it has just found the best result in the vicinity, right? Not over the entire range. So you will get the suboptimal solution, which is not something which you want. So that will be the drawback if something like this happens. But yeah, right now let us understand the terminologies. Then let us move ahead and understand about equality and inequality. So what is equality constraints? Equality constraints specify that two expressions must be equal. So hence equality constraints result in a precise solution. So in the first picture, you see that if there is a line and it is very sure that maybe two equations are aligned and they are equal. So they form or they fall on the same line. So all the results will be falling on the same line. But when there is an inequality constraints, specify two expressions are greater or lesser than, so we have a lot of equations where we say this is greater than that, this is greater, lesser than A. So when those kind of equations come, we will end up in a range of possible solutions. We will not have a very specific point or a very specific line where we can find the possible solutions. We will have a range. So that is how different equality and inequality constraints are. Then when we move ahead, there is another picture representing linear functions and nonlinear functions. I think a lot of people are very familiar with it. In linear functions, the relationship between dependent and independent variable are very proportional. So it always is a straight line. It is a single dimension line. So maybe a equation y is equal to mx plus b is a linear function. So what is a non-linear function? Where the relationship between dependent and non-independent variable are non-proportionals for sure. So what can be a non-linear functions? maybe all these polynomial functions, exponential functions, and the logarithmic functions all fall under nonlinear. So, having known this, let us move ahead and understand the mathematical representation of an optimization. So, the objective function, as we know, is denoted by f of x. So, when f of x is an objective function, the decision variables are the parameters like x1, x2, and so on forms the decision variables, and what we want to do with those decision variables. Whether we want to, how are we going to optimize the decision variables, minimize, maximize, and so on. And the constraints are denoted by g of x and h of x. So they are mathematical equations or inequalities that restrict the solution to a space. That is how they form a bound. So these that is g of x and h of x is the way how we represent the constraints. So the mathematical representation of a optimization problem can be written as minimize or maximize f of x under the constraint g of x and h of x, and a function f of x, maybe f of x is equal to x plus x plus x square, something like that. Yeah. So this is how we formulate the optimization problem. Moving ahead, so yeah, here also I have how do we represent in a better way. We have the equation subjected to constraint and minimize f of x and subject to x being less than or equal to 0. So it is a very simple equation and a very simple expectation of the problem as well. So we want to minimize that function, means if x is equal to 0, the function value is minimum, and the constraint also allows x to be 0. So that is how simple. We need not have any algorithm. I can solve it by looking at it. But yeah, this is definitely not how the real world problems are, for sure. So it is important to note that the mathematical representation of the problem should be consistent with the problem requirements. We have to formulate the objective functions very precisely. That is the major chunk. And also, and the optimization algorithm should be chosen based on the characteristics of the problem, such as dimensionality, optimization space, linear, non-linear, and the presence of constraints, and so on. Because there will be certain algorithms which might not operate under constraints. So there are variations of all of that. So we have to be very careful on selecting which is that optimization algorithm you are going to operate on a given problem and a given data. So yeah, moving ahead, let us understand or talk about categories of optimization. So it can be classified based on multiple factors, like the type of variable, number of objectives, presence of constraints, and so on. So based on that, I have a few listed categories of optimization algorithms. So the objective function, in a single objective function, the objective function should be scalar. It doesn't take any, if it is integer or something else, it will not be called as a single objective optimization. And as well, there will be a set of algorithms which will operate only for single objective optimization, and which is only for scalar. So that is one kind of optimization. And multi-objective optimization, something which is a little complex. So there are multiple objectives that need to be optimized simultaneously, that fall under multi-objective optimization. And the next one is non-linear optimization, which has non-linear constraints. Non-linear constraints fall under non-linear optimization, and integer optimization. So where the objective function will take restricted only for integer values. So these are some common classifications of optimization. Many problems what you might um, formulate can belong to two or more um, uh, than these categories. It can be a multi-objective integer optimization algorithm, of course, that is possible. So maybe also when you formulate, you might come up with different categories of optimization algorithms. So these are few most known. So I have it here. So next, moving ahead, the state of art methods for optimization. So we have known that optimization is used all around us, and there is a lot of experimentations happening around optimization algorithms. So there are various ways how the optimization algorithms are approached. So the first one is gradient descent and its variants. The next is evolutionary algorithms, where you have genetic algorithms, particle swarm optimization, and ant colony optimization, and so on. And heuristics-based method of greedy algorithms, simulated annealing, and so on. And deep learning optimization algorithms, where back propagation, stochastic gradient descent, and so on fall under deep learning optimization algorithms, and reinforcement learning algorithms, Q-learning and SARSA, and so on. So reinforcement learning is a very, uh, very promising area where a lot of people are experimenting, because it is mostly operated with not so great amount of data, but still does a great job. So these are some of the optimization methods on a higher level, where a lot of research, a lot of usage, and everything is happening. So what I will be focusing on is evolutionary algorithms. So moving ahead, so evolutionary algorithms are a little older, older in its gen. It was invented long back, and it is being used as a most prominent optimization technique. So evolutionary algorithms are inspired by the principles of biology, biological evolution, such as mutation, reproduction, and selection. So the main inspiration of evolutionary algorithms is the evolution of humankind, or evolution of every organisms around us. So the main components of an evolutionary algorithm include initial population, uh, starting set of potential solutions, which is usually generated randomly. So initial you should have a set of potential solutions where you're experimenting on. So those form the initial population. The next one is the fitness function, so which evaluates the quality of each potential solution in the population. So whether the two population, or the populate in the full of population space, you select a single population, whether it is fit to be continued in its process for the next steps. So how do we do that? We will have to calculate the fitness function to understand whether it is a population which is survival of the fittest. So that is the survival of the fittest is the method, and fitness function is the what the approaching value for it. So after fitness function comes the selection, the process of choosing the best solutions from the current population for reproduction. So once we have fitness function calculated, what we do is the best fitness function will be selected. So that is how we chunk out the most potential solutions and the most weaker solutions. So there is where the selection comes. The next step will be crossover, the process of generating new solutions by combining two parent solutions. So we have for any new offspring, we need two parent solutions. We all know that. So uh, if you take in the terminologies of genetic algorithms, where you see about chromosomes and genes and so on, you need two chromosomes to cross over so that the next set of genes are formed. So that is a process directly adopted, that is crossover. And mutation, the process of making small changes to a solution. Okay, so how do we do it? We will see next, but why do we need mutations? So it helps to avoid getting stuck in the local minima. Because when you have mutations, you will have a very similar but a small tweak in the gene. So that is a very potential new offspring. So if not, then your the quality of the gene will not be different and strong from the parent gene what you have. So it is very important that you will have the step called mutation. And also it helps to explore the solution space more thoroughly. When you do those small tweaks, you will understand the solution space more better, so that you are not in the local minima, and you also have the entire coverage of the solution space. And then we have replacement. Now, the process of replacing the old solutions in the population with the new offspring. This step helps to update the population with better solutions. Because we run for number of generations, when the new offsprings are formed, we have to replace them with the parent offspring, so that a variety of data is included for the next iterations. Then stopping criteria. It is similar to optimization stopping criteria, where which we have to determine when do we want to stop the algorithm, after how many generations we have to stop the algorithm, and so on. So these fall under the evolutionary algorithm and its components. So there are different types of evolutionary algorithms. Like in the beginning slide, I had an example. So genetic algorithms are part of evolutionary algorithms. They are one of the earliest and most well-known, which has the following process of selection, crossover, and mutations, and which are inspired from the evolutions, genetic evolutions. And the next is particle swarm optimization, where the population-based optimization algorithm that simulates the behavior of a swarm of particles. So each particle represents a candidate solution, and then its position, then it has to figure out and then goes and replaces its position based on its own best solution, and the best solution found by the swarm of particles. So that is one of the most used evolutionary algorithm as well. Then we have the ant colony optimization, artificial bee colony optimization. So why do we have all these names? Is definitely because they are inspired from how those things operate. Because, for example, ant colony optimization is mostly inspired from how ants find their food from their colony where they stay to their food finding place, and what is the shortest distance between that. How I think that is one of the fleet maybe. So it is inspired from that side of the uh, idea, so it is named after that as well. So then we have artificial bee colony, which is also part of EA, which is inspired from how these bees collect the honeys, and which is the best one, and which is collected more optimally, and so on. So these are the types of EA which you can explore based on the problem at hand. But let us talk a little more on genetic algorithms. So these are popular form of evolutionary algorithms. So the component is very similar to that of evolutionary algorithms, what we saw earlier. But there are a few unique terminologies here, like gene and chromosomes and so on. So the main components here are population, so a set of candidate solutions to the optimization problem. Each solution is represented as a string of bits called a chromosome. So a string of bits together will be called as chromosome, and each bit will be called as genes. And then fitness function, the fitness function as similar to the evolutionary algorithm step, we calculate fitness function for each chromosome to understand how strong is it to be selected to go to the next generation. And how do we calculate fitness function? We will see later. And selection process. The process of selecting chromosomes from the population based on their fitness value. Once we have calculated fitness function, we will know how to select or chunk out the most good and a weaker section of the population aside. And then we have crossover. So the process of combining two chromosomes to create a new chromosome. So this is inspired by biological reproduction, where offsprings are created by combining the genetic material of two parents. So the same idea is implemented here, where we will have two chromosomes and we will have a crossover happening. And there are different methods of crossovers which we will look into next, but this is one of the very important steps of genetic algorithm. And mutations, as I told, randomly changing the values of some bits in the chromosome that introduces the diversity in the population, so that it will help us avoid getting stuck in the same specific region and help us move ahead in the problem. So these are a few main steps of genetic algorithm. The replacement is as usual. We will replace the old parents with the new offsprings generated. And this process will be iteratively happening until we find the once we have the convergence of a high quality solution. We have a best optimal solution. So we will also implement how many number of iterations we would need to get into that convergence. Because one thing I want to say explicitly is that genetic algorithms are computationally expensive. So it becomes very critical for you to really put in the stopping criteria. So how do you can play around with the stopping criteria, but how long does the optimization or how long does the genetic algorithm run is something which we have to determine, and we have to find a convergence point. So this is the flow of genetic algorithms. Okay. This is a slide which most I use mostly because when it comes to statistical learning and data science, there is a lot of urge where we will go and implement and just find answers. But we as data scientists are expected to explain the answers what we get. So it is so important for us to really know why, how, and everything about the algorithm. So we will definitely want to know more theory to not fall into the local maximum. So let us go ahead with a little more theory on genetic algorithms. So deep dive into selection, crossover, and mutation. Why do I say that selection or this process of selection, crossover, and mutation is important? Because these are the three very critical things which determine the genetic algorithms. Once if you because genetic algorithms are very sensitive towards hyperparameters, the kind of selection method you use, the kind of crossover methods you use, the kinds of mutation methods you use have greater impact on the result what you get. So it is important that to know how the selection is happening as well. So as you know that selection is a process of choosing which individuals from the current population will be parents for the next generation, right? So there are different selection methods that can be used, such as roulette wheel selection, tournament selection, and elite selection. So let us try to understand the selection methods. So roulette wheel selection, I think a lot of us are very familiar with the roulette wheel. Uh, how does this selection works is when you have a greater region in the roulette wheel, so the probability of that region being found for selection is more. Here they just operate by the probability of that region being found is more. Here we will have a fixed point or a ball like in any normal roulette wheel, and we spin the wheel and the ball falls in some section of the wheel. So to understand roulette wheel, what if the section of the real roulette wheel has different densities of each section? What if the sections are not even? Then the density or the side of the roulette wheel which has more space has more probability that the ball goes and falls there. So the same applies here. We will have the entire population divided based on its fitness values. And when we turn the roulette wheel, the population which has a higher fitness value has more probability of getting chosen. So this is one of the method which is being followed. And tournament selection, this is a very straight away method. There you have a lot of probabilitical possibilities. Then the tournament selection, you randomly choose parents, and from randomly chosen parents you select the highest fitness value and you will select it as the best. And the elitist selection. So this method ensures that the best individual from the current population is always carried forward for the next generation. So in the above two selection methods, there was a lot of probability and random things involved. But the genetic algorithms have evolved to an extent where we are making sure that only the best um, generation or the best genes are carried to the next. Um, how do we do that is a very long process. It is definitely by calculating the fitness score. But how do we calculate that fitness score? Involves a lot of classification, adopting a lot of classification models and so on, which is a part of advanced genetic algorithm like SPEA and NSGA and so on. I will really urge everyone to really look into the elitist selection based algorithms. They really find a good application in a lot of problems. Then the next in the important components of genetic algorithms comes crossover. So crossover is the process of combining the genetic material of two parents to create a new offspring. So like we have discussed before. So in crossover also we have different kinds of crossover, where in the first diagram when you see it, it is a single point crossover. A single point is taken randomly across the parent chromosome, and then it is just shuffled. I think you can see it here how it happens. And the next is uniform crossover. So after each gene from two parent genes are replaced. So uh, this is also one kind of crossover. And there can be multi-point, 2-point, and so on. There are different kinds of crossovers other than this as well. So why does it become, and it is very crucial that what kind of crossover methods we choose, because it highly impacts on the result of the algorithm, as genetic algorithms are very sensitive. Trust me, I have run a lot of genetic algorithms, and it is sensitive to an extent where you will feel like discarding the entire algorithm. So it becomes very important what kind of crossover or any other parameters you choose. Moving ahead, next, mutation. The key idea is to insert the randomness in the gene. That is why we have mutations involved. So here, when you see a neat gene formed is added with two junk values. We can't say it as junk values, but to with new genes to include the randomness. But when you understand the similarity between these two genes, the similarity will be greater, but not exact. So that is how it will help us to really explore the region where this gene might have been formed. So these are the three most crucial steps in a genetic algorithm. So let us understand a little more on genetic algorithm, how it is explained, how it can be started off when you have a problem in hand. So there is a problem, maximize f of x with a function subjected to certain constraints. So here x1 and x2 are the decision variables. And the goal is to find the maximum value of the objective function. So the decision is to maximize the f of x. Then subjected to the constraints, we have this, which has to be lesser than or equal to 0 or greater than or equal to 10. So one way to solve this problem is using genetic algorithm. The steps involved are the steps which I explained previously. So we start with initialization, start by creating an initial population of solutions, each represented by set of values of x1 and x2. So you can randomly add values for x1 and x2 and have an initial population defined. Then you will have fitness evaluation. So why do we do fitness evaluation? Is to select to have the good genes or the good chromosomes for the next. We will do fitness evaluation, and evaluate the fitness of each chromosome in the population by calculating the value of the objective function. We can directly calculate fitness function. It's a very simple way of calculating fitness function would be populate the value and see does it meet inside the constraint and calculate the fitness value. Then selection to really chunk out between the better section of chromosomes and the weaker section of the chromosomes. We go to the selection. Then crossover, where we will exchange the two chromosomes, single point, multi-point, and so on, which we saw in the previous explanation. Mutation, introducing a random changes, and we will repeat the process so that the best chromosomes are come throughout the iterating of multiple generations. So the process of crossover mutation steps to create the next generation. Then termination. Termination, like the way I explained before, termination criteria is something which we will choose when we will have to stop. So repeat the process. We will have a condition till when we will go. When are we going to repeat the entire iterations of our genetic algorithm? And when we maybe if we have our objective function reached, we might terminate the process. Or when we have reached the number of generations, exhausted the number, not exhausted, we cannot exhaust the number of generations, but we can, as it is computationally expensive, we will have a certain number of generations in mind. When we have reached that, we can also terminate the process. So here I have one more solution or a case study where maybe you have a factory that produces three types of products, A, B, and C. So you have a limited budget for purchasing raw materials, and you need to determine the optimal amount of raw materials to purchase in order to maximize the total profit from the sales of the three products. So the profit from the sale of each product depends on the quantity of raw materials used to produce it. So as well as the market price of each product. So the quantities of raw materials used and the market price of each product are given as follows. So these are the information about the raw materials and the market price and so on. So when you get a problem like this, the a very critical step is how precisely you will write the objective function. So for the given solution, I have formulated the objective function as maximize the for variable 1 into 50x, because depending on its price and so on. This was a very easy example, but when you come to critical or complex problem statements, how do you write defining your objective function becomes very critical. And we also have constraints, because the price bound here in this example is defined. So we have a certain constraint also. So this is how a problem might look, and this is the first step how you will start with it. So now when we have talked a lot about genetic algorithms, to have a summary on why I urge or why genetic algorithms are used more is it is very strong where we have more probability of finding the global optima for complex and non-linear problems. When I say multi-objective optimization, it is as complex as you can think of. So in such kind of situations, using genetic algorithms finds its best. And genetic algorithms can handle large number of variables and constraints, because when you adopt different kind of algorithms, not sure, but definitely then genetic algorithms, there are constraint-based genetic algorithms, which really operate under the scope. So it is more robust when it comes to a large number of variables and constraints. Robust against noise and local optima. So as I told you, genetic algorithms has more probability of finding the global optima, as we are it is very eventual, because we are doing all those mutations and crossover operations, which is also involving diversity in the space. It becomes very natural that we will not end up in local optima, and we will definitely explore the space and move ahead to global optima. So then, easy to implement and parallelizable. Uh, Genetic algorithms are definitely easy to implement, because there are these methods are very confined, that you know the steps for sure, these are the steps. And then there are a lot of libraries in Python. I extensively use Python in Python, where you can directly pull in all these functions and methods and implement. uh, and the drawback of genetic algorithm, which I find it is computationally expensive for sure. But um, a solution for that is it is parallelizable. So a lot of operations uh, to find the fitness and selection and so many things can be parallelizable in genetic algorithms. So I think venturing into parallelizing a genetic algorithm is really fruitful. Uh, is really fruitful in really compressing a lot of time it takes. So yeah, when we talk about limitations, it is computationally expensive, sensitive to the choice of parameters, as I was stressing on the point that it is very sensitive to crossover mutations and selection fitness values. So it becomes very critical on what kind of crossover or what kind of selection we choose. So these are the limitations. uh, I have listed here a few genetic algorithm implementation libraries. I extensively use Python, so these are a few libraries which are readily and more diversely used. Deep there are certain more libraries. You can take a note of all these things, and maybe I can drop in a few more libraries which I have tried in genetic algorithm as well. So as we have looked into a lot about optimization, genetic algorithm steps, and so on, I think I was able to give you a small gist on how really, I mean, what optimization is, in where all, which all area optimization is used, and genetic algorithms, the existence of genetic algorithms, the steps involved in genetic algorithms, and where all you really have to stress when you adopt genetic algorithms, and so on. So here I have two real examples. There might be much more than this. I have masked the uh, original company. So a certain aircraft company used genetic algorithms to optimize the design of the wing structure of a certain airplane, resulting in significant weight reduction and fuel savings. And another, a semiconductor manufacturing company, used genetic algorithms to optimize the layout of new manufacturing facility, resulting in 20% increase of in production efficiency. So these two are real implemented examples of a certain two well-known companies in the domain. So why am I quoting this is this doesn't just exist in the theory or literature of data science. Data science and statistical analysis are greatly used, applied, and taken benefit of. So I have a small code demonstration. So here I have not used any libraries. Here I have just implemented code for this event um, to find maybe yeah. So the how the entire process, whatever I have explained in our genetic algorithms, this is the implementation of a basic genetic algorithm. One thing I want to say here is, of course, we have a lot of libraries, but I would still urge that you can use libraries, but you also try to build your own functions so that you have more hold on those functions, and you can dynamically change what the function has to do for you with respect to a lot of functions involved in genetic algorithms, crossover mutations, and so on. This is a simple implementation of finding the problem we will try to solve here is to find the maximum of a 3D function similar to that of a hat. So if you imagine a hat, there is a maximum point in a hat. Yeah, so that is what we are trying to find here. So the first step will be population generation function. We have to have an initial population. So I haven't used any libraries, but you can take use of the same functions later. So I will generate a function. I will generate the initial population in which the rest of the process will operate on. Then the fitness function, it will be our evaluator, which will express how better or worse an individual is from each other. So the individuals with the best fitness should be preserved and should be taken to the next one. So here we will calculate the fitness function. Then we can, after we have the fitness function, we can reproduce the more number of generations. And then how do we select the best of the generation comes in the, okay, I have printed a lot when it is a HTML format. Yeah. Then when we have a lot of fitness function calculated, we will use the selection operator. Here I have used the roulette wheel selection, and uh, we can definitely use different kinds of selection operators. Then the next steps of crossover and mutations. Then once we have crossover and mutations, we will have the final result. So I doubt about my final result, what I have here. I have just run the random code, but the ideally the result is somewhat okay, because it is almost maximum 0.94 something is the best picked, the highest global maxima, the highest fitness value. So maybe there is a better solution above there. I have to pick the right one. So here I have run it for 100 generations, and I just picked something randomly. Yeah, I can definitely pick the better one. So this is how a simple implementation of genetic algorithms looks like. Definitely, there is a lot of improvement in this current code, and similarly, you can implement and similarly, you can try out implementing different using different libraries. So yeah, it was a lot of theory, a lot of generic examples, and a lot of things about optimization and genetic algorithms. But to have a final conclusion, what I want to say is genetic algorithms are definitely powerful optimization technique, and I have given examples where they have been readily used to solve wide range of problems. So they are particularly useful for problems that have multiple solutions or multiple local minima. So they also have the ability to handle constraints and multiple objectives easily. So these are the points which I have stressed from the beginning of the presentation. So however, genetic algorithms are generally slower than the optimization algorithms, than other optimization algorithms for sure, and requires more computational resources. Uh, I am here to not market the genetic algorithms, but to readily say while you explore genetic algorithms, what what are the things happens and what are the things you will face, and how do you to an extent tackle those things. And it's best to use genetic algorithms when the problem is complex, multimodal, and when no gradient information as readily available. Or else, if there is gradient information, there are different kind of algorithms. Those can be readily used than genetic algorithms. So uh, so now when I spoke so much about genetic algorithms, evolutionary algorithms, so which is that best technique, or which is that best genetic algorithm? So it is important to note that the best optimization technique for a given problem depends on problem's characteristics. So how well you understand the problem, how well you define the problem, how well you define the objective function of an optimization problem, and how well you categorize where does this problem fall in. Then you search on which algorithm you have to use for the current problem in hand. So maybe the dimensionality of the problem, degree of non-linearity, and the presence of constraints, and so on. So these are certain examples which I have given based on the classification of optimization, which I had previously explained about. But yeah, the most crucial thing is concisely coming up with the objective function. So yeah, so I hope I was able to touch upon certain things where you can take it from there, about optimization and genetic algorithms. Thank you so much for joining in. And I think we have crossed the time way beyond than what we had. Maybe we can, I have left my contact in the page, so you can uh, ask me, or let's have a good discussion about we whatever we know in the data science. So I'm open for that. Thank you, everyone.